So we're now moving on to our final topic of Year 11 chemistry, which is chemical analysis. Chemical analysis is a wee bit different to the last few topics we've looked at. If you think back, recently we've done the periodic table, acids, bases and salts, and quantitative chemistry. What those topics have in common is they're quite focused on chemical reactions in terms of equations, observations and calculations about those reactions. Chemical analysis is a wee bit different in that there aren't so many actual chemical reactions to look at. It's more focused on how substances behave in general without even looking at their chemical reactions. So the differences between pure and impure substances, how you might purify or separate different mixtures, and how you might test for particular types of chemical within a sample. So there's kind of three main strands to it, to chemical analysis. The first main strand is this idea of pure versus impure and what that means. Then we move on to a subsection called separating techniques, which is basically how do you purify mixtures or impure things. And then the final bit we look on to is how might we test for particular substances or chemicals within an unknown sample. So we kind of got three main strands to look at. So the first part's on pure and impure. So we start with the definition of what we mean by a pure substance. Pure substance is a single element or compound not mixed with any other substance. So putting that into other words, if you've got a container like a beaker and it contains either one element by itself or one compound by itself, you would call it pure. So if I've got a beaker of carbon and nothing but carbon, I call it pure. If I've got a beaker of water but nothing but water, it would also be called pure. If I mix the two together though, it would be an impure mixture. So I'm allowed either an element or compound by itself. If it's a mixture of two or more things, it's not pure. So I might just add a wee kind of contrasting definition. Mixtures are impure. Now, pure is not really a word that's used that well in everyday life in the chemical sense, because lots of things around you will be advertised as being pure but aren't actually chemically pure. For example, mineral water is often kind of advertised as being quite a pure, healthy thing, which is true, but it's not pure in a chemical sense. If mineral water was pure, it would have to be water and nothing but water, a single compound by itself. However, if you look on the side of a bottle of water, you'll probably see something that looks like this. It's the mineral information. These are all the different ions which are dissolved in that water. You've got quite a few there. That means that mineral water is a mixture of things. It's water mainly, but it's also got these different ions dissolved in it, which makes it impure. Other things you'll see that are advertised as pure would be things like fruit juice. They're going to be pure in a natural kind of sense, but they have got lots of things dissolved in water, so not chemically pure substances. So we've got a definition of what we mean by pure and impure. The only other thing to look at in that subtopic is how do we tell pure and impure substances apart, which isn't necessarily as easy as it sounds, because it's hard just to tell by looking at something whether it contains one thing or many things mixed together. Probably not what you expect, but the main way that scientists can actually work out something is pure or impure is by melting it, because you see something quite distinctive when you melt a pure substance versus when you melt an impure substance. There's a difference there. So I'm going to come back to notes in a second. I'm going to kind of illustrate this with a wee kind of thought experiment, which kind of shows you the main point. If I took, for example, a beaker, and inside this beaker I put an ice cube, so frozen water. And at the minute I'm in a very, very cold room. I'm going to say the conditions around this ice cube in this beaker is currently minus 40 degrees C. So it's in no danger of melting in a minute. It's very, very cold. In this thought experiment, what I'm going to do, I'm going to provide a wee bit of heat to this beaker and to the ice cube. Now very slowly, not going to heat it too fast, but I'm gradually going to heat it up and heat it up and heat it up. And I'm going to keep track of the temperature of that ice cube or water as it heats up. Now there's no trick here, it's just going to heat up and gradually melt, and if I heat a bit more it's going to boil. But I'm more interested in how it happens to the temperature as I do that. If I was to plot a graph to show the temperature in degrees C of that ice cube or the water as I provide heat energy to it, I want you to think about how the temperature might increase as you provide heat to it. Now probably what you're thinking in your head is something that looks a little bit like this. Probably would expect just a gradual straight line increase as it gets gradually hotter and hotter and hotter as I provide more and more heat to it. And maybe in some way along this path, I might turn from solid into liquid. So I might get past the melting point and turn it into liquid. And eventually I might go past the boiling point of water, 100 degrees C, and turn it into a gas. That's a pretty reasonable kind of approximation of what would happen. Not actually true though. It's a tiny bit more complicated than that. What I actually would see if I did plot that graph and took those measurements is a graph looks a wee bit like this. So temperature again, heat energy. I'm going to actually put some points on my graph. I'm going to put minus 40 because that's where I'm starting in this particular thought experiment. Going to mark on the melting point of water, which is 0 degrees C. I'm going to mark on the boiling point of water, which is 100 degrees C. At the start, what happens is kind of what I expect. The temperature of the water will gradually increase. So as I provide heat to the ice cube's going to get hotter, simple enough. The difference is when I get to the melting point. When that ice cube starts to melt, the temperature kind of levels out for a wee bit. So we'll go horizontal. The reason it's gone horizontal there is that all the heat energy I'm putting into it at that point isn't going into making the ice cube any hotter, because ice can only get to 0 degrees C, otherwise it's a liquid. All the energy is going into converting the particles of the ice cube into liquid particles, in other words getting to spread out a bit more. So while it's melting, it can't actually go up in temperature. It has to wait until it's all fully melted. Once it is fully melted though, it can start heating up again. So once I've got like a liquid at the bottom of my beaker, it's fully melted, I can start to heat up that liquid and it will gradually increase again. The same thing happens when I get to the boiling point. So when I get to 100 degrees C, I can't get the liquid water hotter than 100 degrees C, otherwise it'd be steam. So all the energy at that point isn't going to make anything any hotter. It's going to go into converting all that liquid into gas. So until it finishes that, it has to remain constant. All the energy is going to changing the state. It can't make the water any hotter than 100 degrees C. However, once I have got it all boiled off and turned into steam, that steam can't get hotter and hotter still. So it's not a million miles away from the first graph we looked at, the simpler one. The only thing we've got to be aware of is whenever we melt or boil something, while it's melting or boiling, the temperature doesn't actually increase. It levels out until all of the substance has actually changed state. So if it's marked on in this graph, before I get to the end of this horizontal section, it's still an ice cube, it's a solid. And it's going to remain a liquid until all of it is converted into a gas past this horizontal section here. So here's the liquid section and the gas section is after that there. So you'll see that same graph in your notes, and again there's not a huge amount of explanation, you don't need to know too much detail about it, but it looks like this, hopefully reasonably similar to what I drew. The key point is, going back to why we're looking at melting points, boiling points, we're going to look at in a second, the melting points and boiling points can be used to distinguish between pure substances and impure substances, always known as mixtures. In general about this graph, just want to focus on this wee point that I emphasised to you earlier. The temperature does not change when the substance melts or boils, even though energy is still being supplied. The reason for that is, again, all the energy is going into getting the particles to change state. So ice cube can't get hotter than 0 degrees C. It can only get hotter than 0 once it's turned into a liquid. Now, on to the main point. How can we tell impure and pure substances apart by looking at their melting points and boiling points? That's down here. Now, there's one wee little side point I want to make here. Questions do occasionally come up in exams that ask you what's meant by the melting point or boiling point. What's very tempting is for you to write the melting point is the point at which something melts. You'll get no marks for that because you just repeated the question back to the examiner. What we mean by melting point, it's the temperature, so the point means the temperature at which it melts. I might even improve that a wee bit more. Melting means changing from solid into liquid. So when we mean melting point, we mean the temperature at which it goes from solid to liquid. If we mean boiling point, we mean the temperature at which it turns from a liquid into a gas. So that's how we properly define it. But what's the difference then? Here's the important point down here. Pure substances melt or boil at specific melting points and boiling points. In other words, looking back to this graph, this is pure water, the graph for it. You notice it melts at exactly 0 degrees C. There's no kind of range or curve there. It's a straight horizontal line at 0 degrees C. It boils at exactly 100 degrees C, so it's a completely horizontal line. The contrast for impure substances is this. Impure substances do not have sharp melting points and boiling points. They melt and boil over a range of temperatures. So what we mean by that is we wouldn't see actually a horizontal line there. We kind of see like a wavy line or a curve because it's not melting at one specific temperature, it's melting over a range of temperatures. That's one of the differences with impure substances. The second one is when you have impurities, when you have mixtures added to a substance, there's a wee mistake in notes here, they actually lower the melting points. So I put that all together. Whenever you have impure substances, there's two differences about their melting points and boiling points. First difference is they now melt and boil over a range of temperatures, and they also melt and boil at a lower temperature. What it looks like is this. So in this purple pen first, I'm going to show you the curve which you should get for a pure substance. So this is any substance, let's say it's melting. I'll get the horizontal bit when it's melting. And the reason I can tell that's a pure substance is that that melting point is a complete horizontal. It's melting at one specific temperature. So the two differences I'm expecting to see for an impure substance, we'll draw on this other pen, is that the melting point should be taking place over a range of temperatures and also be at a lower temperature. Impurities tend to lower melting points, boiling points. What that will look like is like this. At the start it'll be the same, but it's going to start melting sooner, the melting point's lower, and it's going to start melting over a range of temperatures. So it's kind of like a slanted or curved line. So it means it's melting over that range from here to here, not at one specific temperature. So that's how I'd spot in the graph whether I've got a pure or impure substances. The fact it's a range and the fact it's a lower temperature tells me something is impure. Now that might sound a wee bit strange, but it does have a very important use in everyday life. I'm sure you're aware in winter, to stop the roads from freezing over and icing up, we put grit or salt on the roads. Salt works by this same principle. If you add salt to water on a road, you're adding an impurity to it, and impurities cause the melting points of something to be lowered. So if you have salt on the water on your road, the melting point of that water on the road becomes lower. So it's going to melt at a lower temperature. So it might melt, for example, at -3 degrees C as opposed to 0 degrees C. What that means is you can get much colder temperatures that water is going to remain a liquid where it's safe to drive on and it's not going to freeze. So if you didn't have salt on it, if you're at -3 degrees C, you're going to have a frozen road. But if there's salt there, because you've lowered the melting point of that water, the water remains melted in a liquid form. That means it's safe to drive on. So while we're on the topic of melting points and boiling points, there's a little thing on the next page of your notes. I'm not going to spend too much time on it. You cover this kind of when you looked at properties of different types of bonding or structure, where you had to work out from melting points and boiling points whether something was a solid, liquid or gas at room temperature by comparing to the melting points and boiling points. Just explain it very quickly. The key method to working this out is that you're comparing your melting points and boiling points to room temperature. Room temperature is normally described as being 25 degrees C. So if I look at A here, if I compare the melting point and boiling point to 25 degrees C is at a temperature above -100. However, 25 degrees C is lower than 100, so 25 fits in the middle. So if I kind of imagine that's a bit like a temperature scale, if I have substance A, and I gradually heat it up from -100 degrees C. Once I get past -100 degrees C, it's melted, and then I get to room temperature. So at 25 degrees C, substance A has melted, it's gone past its melting point, but it's not yet boiled because it's not high enough temperature to be boiling. Therefore, if it's melted but not boiled, it must therefore be a liquid. So you can pause the video, have a go at the rest of them. I'm just going to write on the answers here in a second. So this is what you should have got. B is a gas, C is a solid, D is a liquid, E is a gas. Now beyond the bottom of the page you've got the description of an experiment to try and see if an impurity does change the boiling point of something. I'm going to skip that now because you're in your house, you can't do this experiment, there's no point doing it right now. Now the last thing we'll look at in this video is this on page 4, this little subsection on mixtures, which still kind of do with pure and impure substances because remember mixtures are impure substances. We've got a few wee definitions which you have come across down in junior school back in Key Stage 3, but they do kind of come up again in GCSE. Just make sure you're still happy with them. So first of all, a mixture is defined as two or more substances mixed together. Substances can be elements or compounds. If there's two of them, it's a mixture. Substances are easily separated because they are not chemically joined to each other. If they're chemically joined to each other, they're now in a compound, not a mixture. Solids that dissolve in water are described as soluble, and solids that do not dissolve in water are described as insoluble. A solid that dissolves, you might be less familiar by this word, is known as a solute. So if I take salt and dissolve it in water, I'm describing the salt as being the solute. The liquid in which the solute dissolves is called the solvent. So in that same example, if I dissolve some salt in water, I'm describing the water as being the solvent. It dissolves the salt in it. Tricky wee question down here, what's a solution? Technically there's a definition for that. Solution is just a solid dissolved in water, but putting in our slightly more scientific words, what we really mean is it's a mixture of a solute and a solvent. So there's a few kind of definitional words to be aware of, make sure you understand them within the exam. Last little bit of mixtures is kind of another little definition of formulations. Now more than likely you probably haven't heard the word formulation before. A formulation is a type of mixture, but the difference is it's a mixture is actually be designed with a purpose or to be a useful product. So it's not a random inconvenient mixture you might have. It's like putting a mixture together for a particular purpose or product. So you've got a definition here. It's actually quite a long definition. It's actually these 2 paragraphs put together. Normally it can be a 3-mark definition. A formulation is a mixture that has been designed as a useful product. It's formed by mixing together several different substances in carefully measured quantities to ensure the product has the required properties. What's trying to get at there is it's not like just mixing together a thing randomly and seeing what happens. It's really carefully designing how much you put of each substance in your mixture to make it do a certain purpose. They could ask you for an example in the exam. There's plenty of examples. Fuels, cleaning agents, paints, medicines, alloys, fertilizers and foods, they are all mixtures of things, but carefully designed mixtures to be good at their job. To show one example I had in my house, here's Lemsip. It would be a good example of a formulation. How you can tell it's formulation, it's doing a job, it's to help you if you've got a cold, and also it's a mixture, because if I look at the ingredients list on the back, it tells me it's got paracetamol, phenylephrine hydrochloride, sucrose, lactose, sodium and aspartame. Each of these things has a different job to do. Paracetamol is a painkiller, stops you getting a headache. Phenylephrine hydrochloride is a decongestant to stop your blocked nose. The problem with paracetamol and phenylephrine is they're quite bitter tasting drugs. So we've got sucrose and lactose, which are 2 types of sugar, to make it taste a wee bit more sweet so you can eat it without throwing it up. So it's illustrating the point there that you have a mixture of certain substances together, but they all have their own role to play, and it's been put together in specific quantities to be good at that job, thereby making it a formulation.